Okay. Alrighty. Alrighty. So the first thing I wanted to do is start off with asking if you guys had any questions about the course or the syllabus. Feel free to just unmute yourself. I don't like using the chat because it sort of gets hidden away under like the applications and stuff. So if you have any questions, feel free to just unmute and ask away. Otherwise, we'll sort of go ahead and get started.
Hello, Professor.
Hey, how's it going, Matthew?
Good, how are you, sir?
Yeah.
Could you just speak to, I guess, your opinions on the difficulty of this course, or what kind of work we should be expecting to put in, apart from like the 10, 15 hours on the test and the syllabus?
Well, I mean, it's like a normal course. I wouldn't think it's particularly crazy or particularly easy. So I think
Okay,
yeah,
sounds
yeah,
fair enough. Thank you so much.
yeah. So I wouldn't put it. Yeah, this is absolutely not a class where I would say, oh no, this is easy, you don't do any work. Nor would I say, or not any work, but the
Right,
type of learning is time intensive. But on the other end, I would not say that this course is extremely time intensive. I think where students have the most amount of issue is just managing how they dedicate their time. Um, and usually the biggest issues is where, and I think I sort of mentioned this in the video, one of the other videos, is students wait till the last week or the last day to complete major assignments, right? So if I give 10 days for an exam, you should pretty much expect to use 2 or 3 days to do that exam. So if you're going to just spend one day on the exam, that doesn't make any sense.
right.
You're going to do pretty badly. So it's not, yeah, so it's not particularly crazy. It's just, I think some students have difficulty recognizing they need to start early on their assignments. And the same thing goes with the project. Every year I get complaints of, oh, we needed more time with the project. And in fact, the project isn't more intensive than 2 or 3 homework assignments if you're keeping up with the class. But the problem is a lot of students don't keep up with the class. And so then the project comes along and they try to do it in 1 week and they try to watch 3 to 4 weeks of videos in order to do the project. And so that's where students get in trouble. And so, yeah. So that's
Fair
what I'll
enough.
say to that. So yeah. So I think as long as you stay on top of watching the videos and stuff like that, you'll be fine. I'm not concerned at
Got
all
it.
with the vast majority of students.
Okay, great. Thank you.
Yeah. Any other questions? Okay. Alrighty. So, I do want to sort of address the course modality, and I sort of put this in one of the announcements on why we're doing what we're doing, and my goal is, no matter what, to allow everybody to watch all the videos, regardless of what happens, right? Whether they get sick or not get sick, or whether they're working remotely in the middle of the desert in nowhere land, or if they're on campus. And the reality is, every year we get that complete span, right? So we had some folks working off at a testing range. And for them it was a lot easier to download videos and stuff like that because they rarely had access to internet. They're literally living in a trailer in the middle of the desert, right? And then also I think just practically speaking, people will get sick in this class, unfortunately, and hopefully it's not too bad. And so I really want to make sure that all students can access the material, right? But the additional difficulty is that a lot of this class will involve working with software called Simplex. And we're going to spend a good bit of time learning how to program in Simplex. So Simplex, it's not, for those of you who aren't industrial engineers and you've never taken an optimization class, Simplex is basically how we program up an optimization program. So it's just the mathematical formulation and putting it into a piece of software. It's not like you know, Java programming or Python programming. It's a completely different beast, right? So if you struggle with Python programming or, you know, Java programming, that's fine. This is not what we're talking about. So this is linear programming and optimization programming. It's a different type of programming. But nonetheless, it does involve working with a piece of software. And oftentimes, it's better if I make very tight pre-recorded videos on that content, okay? Because in the past, I tried to lecture it live, and it's one of those things where, like, if you miss a semicolon or you misspell something, then you spend 20 minutes trying to figure out why the code's not running, right? And so in order to just make an effective use of our lecture time, it makes more sense to put some videos and record them in YouTube, or make them accessible. And YouTube's sort of the best way of doing that. And sort of the complaint last year was we had like Panopto videos, we had Zoom videos, we had YouTube videos, and students didn't know where to access information, which was absolutely a fair critique. So this year, I'm going to try to put all the material in one location, or multiple, well, one location as in YouTube, but you can access it through different ways. So if you want, you can just subscribe to my YouTube channel or the playlist, and you can watch the playlist get populated and you can watch videos. Or I'll also put links to the YouTube videos in each unit. And hopefully that works out well. You know, I'm going to try to, as needed, I might need to split up videos, right? So if we have a lecture that covers 2 units, then I might have to stop. And you'll probably see me say something like, I'm going to be quiet for a minute. And then we'll be quiet. And then I'll know that's sort of like the cut point. And then I'll try to put the rest of the video in YouTube. So again, it's going to be a little bit weird. You know, all I know is what I did in the past did not work. And we're trying to make things better. So this is a step in that direction. And then finally, I think I noted the last issue, which we will absolutely probably run into today, is my Zoom is a very resource intensive program. By itself, and like a simple PowerPoint is usually not too bad. But when I start using OneNote and definitely other applications, my Surface, my Microsoft Surface starts to overheat, and then at some point it just won't work. And last year I used to curse during lecture, and apparently some students were offended by that. So this year I will just sort of wrap up lecture once my computer starts overheating and becomes unusable. And so that's the other reason why we might have some recorded videos. So I think that the most likely process that we're going to see is, again, I'll do everything on Zoom. I will always hold lecture, or we'll say recording time, starting at 1:30. And I'm just going to try to record as much as possible before my computer shuts down. And then usually what I'll try to do, depending on what it is I might record it, the remainder of lecture during the weekend and then post it. Or I might try to do the remainder of the lecture on like Monday. And I'll see if I can set a time. So depending on what sort of response I get from you guys and what works best, we'll sort of take that approach. But absolutely, I would like it if you guys could attend lecture, right? Like whether virtually or live, doesn't really matter. But yeah, so that's sort of the lay of the land. And again, if something's particularly difficult or challenging, or you really don't like, after good, we'll give this like a week or two to see how things go. I welcome suggestions. Again, it's a little bit hard because I think a lot of times students think this is easy for us on the faculty side, but it really does present some challenges, technological challenges. But hopefully we'll work through it. And yeah, again, just if something's going on that you'd like to communicate with me about how this class is structured or given, yeah, send me a message. I'm happy to chat about it, and I can see how we can make things better. Okay. All right. So and actually, I'm trying something out new today. I jacked up my AC, or jacked down my AC to like 69 degrees, so I'm very cold. But hopefully that helps with the overheating. Maybe I can get some more time out of lecture. Okay. So today is not a particularly interesting day, unfortunately. We're mostly going to be covering some, it'll be like a little bit of a math review. And some of the stuff that we're going to be going over will be very important, especially in the middle of the semester, with some of the techniques that we're going to learn. And so, you know, if you have very strong linear algebra skills, that's fine if you want to sort of fade into the background, or if you're going to watch this video later, watch it at 2x speed or something like that. And then, you know, slow down at the parts where you think it's a little bit more interesting or you haven't heard some ideas. And yeah, so we'll sort of go from there. The last sort of comment, and I said this at the beginning, but if you have a question, don't put it in the chat, just sort of unmute yourself and speak up. And it's not such a big deal if you know, don't think that you're interrupting lecture. I think it's better if you guys are able to interact with me as much as possible. All right, so we're gonna go ahead and get started. Oops, I'm gonna share. Yeah. So typically, just as a heads up, typically what we'll do is, you know, I'll release all my lecture notes. The lecture notes actually do pretty good justice to what I lecture on, but I think there's always additional stuff, sort of my comments and interruptions that are a bit more valuable. But, you know, worst case scenario, the notes I think do a pretty good job for some of the stuff. Okay. And then we'll do some stuff that's not in the notes. Usually, again, like a lot of the programming stuff doesn't really lend well to notes, so it's more for the videos. All right, so I'm going to try to do this as best I can, and I'm sorry you're going to get a good view of my double chin for a lot of lecture. Okay, so today we're going to sort of do a math review, right? This class is pretty intensive, or more intensive, in terms of the math. The sort of math we draw from the most is going to be linear algebra. Okay, so most of what I'm going to talk about today is some of the basics of linear algebra, but then we'll get into, like, you know, null space and, you know, things like that. So and independence, and because these will be ideas that will be a little bit more useful and helpful later on. Okay, so let's see if I can get this to work. Okay, awesome. All right, so first, you know, just as a very basic, I know everybody knows this, but just to get where we need to get to, you know, we're going to work with a lot of matrices and vectors, right? You know, matrix are sort of these block guys, right? So 1, 5, 3, 2.8, right? And of course, they can be of arbitrary dimension. They don't have to be square, right? Okay. Typically, when we reference these, you know, we'll sort of say this matrix is in R2 by 2. Okay, so there's just a fancy script R that's going to be useful to know. And this R just stands for reals. Okay, so basically we have a matrix full of real numbers that is of size 2 by 2. And so there's the traditional notation that we'll use. You know, so this guy would be R 2 by 3, or 2 by 4, sorry. Okay. And certainly we can sort of represent vectors the same way. Usually people just get a little bit lazy, right? So if you see a vector like that, oftentimes people will just represent it as R2. So they sort of drop the idea that you have multiple columns and they just report the number of rows. You know, sometimes this gets a little bit confusing depending on how the orientation of your vectors. Right? So in this case, you know, if you do want to specify a row vector, a lot of times it is sort of encouraged that you denote it R1 by 2. So again, the general notation, if we just want to baseline ourselves, is R represents the reals, and then we're going to talk about M by N. Okay, so where M is the number of rows in the matrix, and N is the number of columns. So we're always row by column. Yeah, row and then columns. The order of the matrix, is this M by N, right? So sort of notation. Okay. This is going to come up all over the place. I'm not always the best about like remembering like, oh, an M by N matrix multiplies times an N by L matrix and stuff like that. But, I know I don't have the best memory of those rules, but they are going to be useful. And keeping track of dimensionality will sort of be an important part in order, if you really want to sort of get good at this optimization stuff. All right. So, a little bit more generally, when we talk about a matrix, let's say we have some big old matrix, and each element we can, going from left to right and top to bottom, we can sort of represent it by the individual values in the matrix, right? So a lot of times you'll sort of see this notation where A1, A11, A12, all the way to A1n sort of represent the values. They're the variables that represent the values inside of the matrix, right? And so you just increment down the indexing. So we can, it sort of goes all over the place. And again, we're still using the same notation, right? So we have n columns and m rows. Sometimes you'll see folks, when they define a matrix, they'll sort of say, well, we have this matrix A, and it has values Aij inside of it. Okay, so these are sort of two equivalent statements. And in fact, you could make it, they're not exactly equivalent right now, but certainly if I say that the A matrix is an element of real M by N matrices, then these two statements sort of become closer to equivalent, right? So mathematically, these are sort of saying the same things, right? They're telling us we have a matrix of a specific size, and we're sort of indicating the names of the values inside of the A matrix. In some cases, depending on your field, sometimes this is actually replaced with an equation. Right, so as an example of that, maybe we have something like -1 to the I plus j power, okay? And so, we could sort of figure out what this is. So, that would be a shorthand way of saying, I think we'd have 1 squared. Yeah, we'd have like an alternating matrix like this. So if you were to tell me that A is a 3 by 4 matrix where the values of A are given by -1 to the I plus j power, then I would know, oh, that's what this means, right? And we do this especially with large matrices, right? It's easier to write out an equation like that than to write out a whole matrix of positive and negative ones. Sometimes people will denote it a little bit differently. So you could also do something like Aij. So if you have a more complicated one, you can certainly break it out. So that'd be one way you could do it. And let's say A was a 5 by 5 matrix. That would sort of imply that, if we were to write out what A actually was, you'd get something like this. Let's see. So this sort of skill is going to be quite useful if you, as we sort of set up these optimization algorithms, sometimes we'll have very, well, I don't want to say complicated, but we'll have funny looking A matrices that we need to use, and we'll define them according to, sort of an equation. So here goes sort of another example where the row index and the column index of each variable, if it's within 1, then you put a 1 there. If it's not, then you don't. So, here, I is equal to 5. Yeah, 1, 2, 3, 4, 5. And j is equal to 1. And of course, I minus j, if we take the absolute value of that, that's 4. So it doesn't satisfy this criteria. And that's why we don't put a 1 in there. So again, this is more useful as your matrices get really large. We're going to come across a number of sort of commonly used predefined vectors. And certainly you guys know of some of them, right? So I think the identity matrix is the most common one. So, we can call them predefined vectors, right? So the ones that we kind of want to be aware of course, we know the identity. This one's pretty easy. And just, right, 0 everywhere except along the diagonal. Right? Sounds pretty good. The other ones that we're going to use quite a bit in this class is the 0 vector and the 1 vector. The 1 vector all over the place. 0 vector, not so much. So usually people bold it, and this just, maybe they'll put a cross through it. This is just a column of zeros. Okay. Similarly, we have the 1 vector, okay, and usually, again, it's typically bolded. And this is just a column of 1 values. Right, so, literally, it's just 1, 1, 1, 1, 1. Okay. So these are 2 sort of vectors that we're going to see a lot. Okay. Now, hold on 1 second. I feel like my notes just got out of order. Okay. All right, so all right, so we got those guys. All right, so the next thing we probably want to talk about are all right, what are some basic math operations, right? And again, this should be a replay for most people, but hopefully I'll intersperse it with some stuff that you guys already know. So we're going to start with this concept of multiplication, and certainly multiplication exists in many different ways. The first sort of multiplication that we can think about is sort of the dot product, right? Right. So if we have two vectors u and v, and we multiply them together using the dot product, this is just given by the sum of all the individual elements of each vectors multiplied times each other. And of course, u and v need to have the same dimensions. And I should be careful about keeping my notation consistent. All right, so alternatively, we can write this dot product in a different way. We can write it as a multiplication, and we'll sort of review what multiplication is again, a matrix multiplication. So it can also be written as U transpose V or V transpose U. So these are sort of, the standard mathematical notation. And we also have the option of representing it as an inner product. But we'll sort of jump into that in a second. So again, this shouldn't be, too hard for everybody. So if we have U, that's 1, 2, and we'll say W is -1, -2. All right, so if I want to just say, okay, what's the dot product of U and W? I'm just going to do a element-wise multiplication. So 1 times -1, and then 2 times -2, right? So, and that's essentially applying this equation right here. So we get 1 times -1 plus 2 times -2. And you add that all up. So -1 minus 4, -5, yeah. So whenever we do a dot product, we end up with a scalar value, right? This is sort of important to, like, I know it's silly, but it's sort of important to recognize. And that's sort of what allows us to make this comment, okay? Because if you take the transpose of a scalar value, you just get back the scalar value, right? So if I do, what's the transpose of the number 1? Well, I get 1 back, right? Later, so as an aside, this becomes a bit more useful when we start talking about quadratic equations that we can represent as x transpose q times x. So this will be a vector. This will be a matrix. And this will be a vector. And the end result of this multiplication will actually be a scalar value, right? And you're going to see it's going to become sort of useful where we can say, oh, we can mathematically beneficial sometimes to take the transpose of this big ugly thing, because that's just equal to the big ugly thing, right? And again, this is because the end result is a scalar. It's a single value. So if you take the transpose of a scalar, you just get back a scalar. Yeah. Okay, so we officially remembered how to do a dot product. Again, sort of when we're working in the Euclidean space, so like with normal vectors and values like this, then this scalar product, this dot product ends up being the same as an inner product. So in the Euclidean space, let me write that down. the dot product is the same as the inner product. Okay, so what's the inner product? Well, you guys probably see it written sort of like this. So if we have two vectors, right, and we put them in these little like brackets, that's the inner product, right? So in the Euclidean space, it's defined as the dot product, right? So this is the inner product. So for those of you who've taken like advanced differential equations, I think sometimes you see that this inner product are actually functions, right? So instead of being defined on the Euclidean space, x and y are functions that you're taking the inner product of. But in our case, you know, we're doing it in the Euclidean space, so we're doing it with vectors. That's kind of, you know, just an aside that's worth knowing about. And again, you know, for those of you who continue in your graduate studies, especially in optimization, you're going to see all these different types of notations, right? So a lot of times folks like to use this notation when they're writing out their formulation. So it's good to just get refamiliarized with it and acknowledging, you know, what it means and how to use it. Similarly, sometimes you'll see folks who use the inner product as part of their formulations. A little bit less common, but it does happen. You know, I always like talking about the inner product a little bit because I think it's sort of interesting to sort of understand like what a inner product space is and like mathematically what does it mean. And so I'm going to spend a quick second on that. So an inner product space, whether it's the inner product of functions or whether it's the inner product of vectors and stuff like that, or matrices or something, they all satisfy some basic rules, okay? Or they have some properties. Okay? So let's see. Okay, so the first one, well, first we have to define what we're doing. So in when we're working in the Euclidean space, so if we have, you know, the following vectors, x and y, and we're going to say both these are x, y, and z, and all three of these vectors are in the space Rn, okay? And we're also going to say there's a scalar. And we'll just call that scalar A. And this is just a real number. Okay, so it's a scalar real number. So it has a number of properties. The first one is conjugate symmetry. Conjugate. And basically that just says is if you take the inner product of the vectors x, y, that's sort of equal to the conjugate of the inner product of x and y, right? So, yeah, so this is sort of a neat little rule. Now, in our case, that's sort of the equivalent of saying, you know, and again, this is sort of a specific case. So this conjugate symmetry, this will apply over any space that you're doing it in, whether it's over functions or anything else. This is the rule. But how does it apply to vectors? Well, that's basically the same thing as saying like the inner product of x and y is equal to the inner product of y and x, right? So this is sort of what I mentioned earlier, right? Since the inner product on vector spaces is x transpose y, that would be equivalent to saying that's equal to y transpose x. So that's sort of a neat little property, or a baseline property that we need to start with. All right, the other one is linearity. Okay. And linearity just says, well, if you have a times x and you're taking the inner product with y, then that's the equivalent of a times the inner product of x and y. Okay. Similarly, yeah, so and this sort of makes sense, right? So if I want to say, like, let's take the inner product of 5 times x and multiply it times y, and so this ends up just being the dot product. That's the same thing as saying x transpose, oops, well, I'll just separate it, yeah, times y, right? So right, and this quantity here is the inner product, okay? So that's all we really say. We also see linearity sort of pop up. The extension or corollary of this is that if you have two vectors, x plus y, and you're taking the inner product with the third vector, z, that's just equivalent of the inner product of x and z plus the inner product of y and z. So this sort of gives you your distributive property, right? That we normally see with vectors. So again, if we want to put this in vector words, right, we have some vector x plus y, and we're going to take the dot product with z. Well, that's just the equivalent of saying x transpose times z plus y transpose times z. Okay. All right, so the last sort of property of these inner product spaces is they have to be positive definite. So positive definite just sort of means that if you multiply two vectors or two values times each other, then you're always going to get a positive number back. Okay. This actually comes up in a few places. You can actually talk about matrices that are positive definite, and this is something that we'll do later on in the class. We'll talk about positive definite matrices. So all it says is if you take a vector and you take the inner product with itself, so if you multiply it times itself, then that's just greater than or equal to 0. And this is only true, though, for all x vectors that are not equal to 0. So if we want to write that. So basically the idea is the only way you can ever multiply something by itself and get 0 is if that something is 0. Okay. Yeah, so the implication is if you ever see the inner product of x and x with itself at 0, then that must mean that x is equal to 0. Okay, so that's sort of yeah, a little trick. There's also others this derivation is actually sort of neat, I think. So, there's other sort of neat properties, which if you take 0, the inner product of 0 and 0, well, that's the equivalent of taking the inner product of 0 and x, 0 times x, right? And this just follows from linearity, right? And based on linearity, you can pull out one of the zeros, right? Okay. And we know 0, so the value 0 times anything is always going to give you 0. And so this sort of tells us why the only way, why 0, the inner product of 0 with itself is 0. So it's sort of like weird, sort of silly, makes sense. Anyways, and then, there's also other neat little tricks that are worth sort of understanding. So if you have x plus y and you take the inner product with x plus y, if you sort of apply this distributive rule that we end up getting, you end up getting essentially like what is the binomial theorem, right? So if we're sort of going to factor this out a little bit, it's the same thing as x taking the inner product of x and y plus the inner product of y with x and y. So again, all I did is sort of split this part up right there. And again, we can sort of apply that sort of distributive linearity rule again. So here we're going to split up this guy into two different sections. Okay. And then the sort of other rule that, again, if we apply that conjugate rule, right? And so in our particular case, these two guys are equal, right? The conjugate. But really, it's the same thing as saying x transpose y is equal to y transpose x. And so because we have the conjugate over here, we can sort of add these two guys together. So we end up with x times x, or the inner product of x with itself, plus 2 times the inner product of x and y, plus y and y. So this sort of looked like a quadratic equation, right? So you got that going on. Anyway, so there's lots of fun math stuff. And again, I'm not saying that we're going to be using this math throughout, but I think refamiliarizing yourself with it sort of adds a richness to the material that you're going to be learning, right? So, particularly what I'm talking about here, it adds a richness, but it's not necessary for you guys to understand it. So don't be too worried about that. Okay, so we figured out how do we do the dot product or the inner product between two vectors. The next type of multiplication that we're interested in is, of course, matrix multiplication. Actually, yeah. All right, so if we have two matrices A and B and we want to sort of multiply them together, so this is what we're going to be talking about. Usually we just denote this as AB, right? So we have we drop this multiplication symbol. I don't know if that makes it easier or not, but usually that's just the way we see it. Okay, so again, I think everybody should know matrix multiplication, but some of the stuff I'm going to show you is just how to think about it in a little bit more of an operations research way, the notation in particular. And so again, you shouldn't be learning anything too new of how to do it, but just how to represent it and think about it is the more meaningful part. All right, so let's say we have C is equal to A times B. Okay. Of course, we could just say C is equal to IJ. Right? And let's say it's, we're going to make this comment given that A is in the reals and it's n by m. Okay. And B is also in the reals, but it's going to have a different dimension. It's going to be O by n. Okay. So let's, the way that I always like to think about it is visually, I think of A as a bunch of row vectors. Okay, so we have row 1, row 2, all the way to row n. That's a little dot, right? So I just draw, some students have gotten confused in the past. For me, I just draw these lines right here so I know it's like a row. Okay, that's it. It doesn't mean anything. That's just my own personal notation. Usually, and it's like a visual sort of representation for me. Okay, people don't do that. I think I'm the only person I know who does that. So usually you just see like A1 dot, A2 dot, A3 dot. And people sort of know that, okay, these are row vectors. Okay. So similarly, we can sort of think about B in the same way. And of course, I have my little trick of thinking about it because it helps me remember how things sort of work out in the multiplication space. So we have B dot 1, B dot 2, all the way to B dot n. Okay, and again, my little notation just to remind me that these are column vectors, I sort of write them that way. Okay, and so B is going to have n column vectors. Okay. And this is the only way that this multiplication works out. And if we think about our A matrix as being these row vectors and our B matrix being these column vectors, then it's pretty easy to say what Cij is equal to. So in that case, Cij is just equal to the dot product of the ith row of A with the jth column of B. Okay. So a lot of folks, for me, it's not so natural to think about multiplication this way, but in OR, a lot of people do. So, for what it's worth. So if you do a lot of operations research, I think sort of this notation or this idea of applying row and column vectors is very, very common when formulating problems. We'll see some of that here, but not nearly as intensive if you go into like research in this area. And it mostly has to do with what we're going to end up learning. So later on, we'll talk about basis vectors and, all the algorithms are sort of based on this notation of basis vectors. And so they're going to talk about, hey, the ith basis vector, the jth basis vector, right? So usually, if you do go into operations research or you do a lot of optimization, it's very useful to think about matrices as a whole bunch of row vectors or column vectors. Okay. All right, so I just want to do one quick example, right? Because I think everybody knows how to do multiplication, but just in case, let's say we have some matrix, 1, 1, 2, 2, 1, 3, and then we have our B matrix. And again, the sort of trick here is that they have to share one dimension in common, right? Which is, I guess, the number of columns, which is m by n, right? And here, the number of rows, right? So that's equal to n. Okay. So in this case, that's why we see that in the dimensions of A and B, they have to match. And again, that's the only way this inner product or this dot product will work, is if they both have the same dimensionality as the number of rows and the number of columns. Okay. So that's what we see in this case. So if we want to go through and sort of figure out what all these, what is C? What is C if I do A times B? And of course, we could say, well, what's C11? What's C12? C13, or not C13, C21, and C22. Okay. And again, this is just a whole bunch of dot products. Essentially, what we're doing is we're taking row times column to get one value, and then we're going to do row times column to sort of get this value here. And we're going to keep going through that process in order to get all the values. So we'll take the bottom row times the first column. That will give us C21. So again, this row times column idea shouldn't be new to anybody, but maybe just a little refresher. So if we want to figure out what the first value of the C matrix is, it's just the first row times the first column. And we get the value of 5. Okay. Similarly, C12, we do row times column. So we're going to end up with a 2 by 2. So we're going to stick 5 in here first. Is equal to 8. Right, so we stick 8 in there. And we just go through this process, right? So row times column, row times column. I'll just do one more just for fun. So now we're going to do the second row, 2, 1, 3 times 1, 2, 1, and we get 7. Okay, so certainly we have MATLAB and tools and our calculators to do multiplication for us. Yeah, I think, again, the idea is here to think about multiplication as a bunch of dot products between vectors. Okay. Okay, so the next thing we'll sort of talk about, and we've sort of come across this, is what is the transpose of a matrix. Okay. So usually, if we're going to use the same notation that we used before, where we say A is some matrix that's filled up with these aij's, okay, so a whole bunch of values. Well, what's the transpose of A? Right. Well, the transpose of A is just equal to AJI. Okay. So this is the equivalent of sort of saying, oh, you're flipping it across the diagonal. Okay. So, if we want to see how that actualizes with sort of an example. Right. So if we end up taking the A transpose, we're going to flip the dimensionality as well, right? So we're going to get A11, A21 here, A12, A13, A22, A23. Yeah. So again, we're sort of flipping across the diagonal. If you sort of follow this idea around, it sort of follows that the transpose of the transpose is your original matrix. So to put that another way, if I take A transpose and then I take the transpose of that, well, that just gives me the original A matrix. So this is our transpose. And again, to sort of be clear, right? So if I sort of said, if you have a scalar and you take the transpose of it, you get the scalar back. And that sort of makes sense, right? So if I say A is equal to the value 5 in a matrix, it's a 1 by 1, okay? And I say, well, let's take the transpose of A. right? Well, that's just still 5. That doesn't change the value, right? And it's a 1 by 1. So again, just trying to drill it into your head. If you take the transpose of a scalar value, you're just getting that scalar value back. Just a pretty useful thing to remember. Okay. We've actually done pretty good. Man, the computer's running reasonably well. All right, so what we're going to do is I've been lecturing for about an hour. I want to give some time for my computer to sort of cool down a little bit, and we're going to take a little break and then proceed. So I'm going to pause with the recording, and I'll let everybody take a little 10-minute break. So I'll get started back up at 2:38. So if you want to step away and go to the bathroom or something like that, feel free. All right, we're going to go ahead and get started back up. So the next thing we sort of want to talk about are matrices and their relationship with systems of equations. Okay. Matrices. And systems of equations. All right. So, again, you guys should know how to solve systems of equations, and I think you've done the Gauss-Jordan method, but we're sort of going to take it up a notch in the class because a lot of operations research, and in particular the most famous algorithm called the Simplex Method, has a very strong relationship to the Jordan or Gauss-Jordan method, and sort of the ideas of like, when do we have multiple solutions or one solution or an infinity of solutions and stuff like that. And so it's definitely worth going over, right? So, yeah. All right, so the first thing that we're going to do is we'll just sort of start off with, all right, what's the basic problem that we need to represent? And so the basic problem is, all right, we have a set of m equations with n unknowns, right? So we're going to have a system of equations. So we have some system of equations. And of course, we're going to be able to tie this back into like a matrix representation. So that's, part of why we talk about how do we represent matrices and the AIJs and stuff like that. All right, so we have this sort of set of equations. So here goes our first equation, which takes into account, a number of a linear combination of different variables, x1, x2, x3, x4. And each of these, as I'm representing them, are scalars. Okay, so there's no matrices yet, but what they end up doing is inducing a matrix equation, of course. So our next, equation, we can write that down as well. And certainly, so we're going to end up with m of these equations. All right. So again, we have m equality equations. And each of these has n unknowns. And of course, those unknowns are x1, x2, all the way to xn, where each one of these is just a real number. Okay, so these aren't matrix equations. These are just sort of standard basic linear equations. Okay. Of course, these are, this is going to set up sort of a matrix equation if you want, right? So like in matrix form, we would just write this as AX equals B, right? So this is sort of the simplified representation where the values of A, the big A matrix, right, just come from A11, A12, all the way to A1n, and then down to ANN, okay? B is going to consist of all these B values, right? So we have B. So B is going to be a vector. Our A matrix comes from all these values. So this shouldn't be anything that you guys don't already know. And then, of course, we have our X values, the unknowns, which again are just going to be represented as a vector later on down the road. Okay. So, but for now, let's sort of, we've got this guy, right? And so I'll be a little bit more explicit about this in about a second. And what we're trying to do is we're trying to find the set of solutions, okay? And the solutions are basically sets of x1, x2, all the way to xn that satisfy the equations, right? Now we have a few possible options, right? We could have no solution. Okay, so there's no combination of x1, x2, dot, 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 xn that satisfies the equation, all right? The other option is we have one solution, right? And then we have a third option, which is we have an infinite number of solutions. Yeah, so this is sort of neat. I mean, I think it's sort of neat because you go from 1 to infinity, right? There's nothing in between, but I don't know. It's just neat. Okay, so again, of course, I sort of already said this. We know we can write the system of equations in matrix form, right? And so certainly if we were to do that, it's just how we've represented the matrix already, very conveniently, right? Where we're just pulling out all the values of the equation. And so this would be the corresponding A matrix. Our B vector would just be the values B1, B2, all the way to Bm. And of course, our X vector would just be x1, x2, all the way to xn. Okay, so just, again, be careful. M is the number of equations, n is the number of unknowns. And so we just have to be aware about that. And of course, this is where AX equals B represents the same system of equation. Okay. So we actually, somebody very smart, much smarter than me, came up with a way of solving the system of equations. Okay, so there's the Gauss-Jordan method, and everybody should have learned it in their sort of introduction to linear algebra, right? Because it's very methodical, right? It's a procedure, more or less. And it's just a procedure for solving systems of linear equations, right? So, sorry, this says lin, like Lin, because I'm too lazy to write linear. Okay, so it just solves, a system of linear equations. And Jordan-Gauss is important for optimization because it's essentially the foundation of the simplex method, all right? And this is what we're going to spend quite a bit of the semester working on, simplex method. And in fact, the simplex method also feeds into a number of other optimization techniques like Danzig-Wolff and Bender's decomposition and all this stuff, which are used to solve large-scale problems using decomposition methods. And like all of them trace their roots back to the simplex method, and even before that, of course, the Gauss-Jordan method. Right, so it's super important, right, to understand simplex method. But in order to understand simplex method and some of the reasons why it works, it's sort of useful to understand Gauss-Jordan, or at least re-remember it, right? Like, again, not anything particularly crazy or spectacular, right? But this shouldn't be the first time you're seeing this material, but certainly I think it's a good idea to get sort of a refresher of what the Gauss-Jordan method is and how to do it. Right? Okay, so the Gauss-Jordan method is based on this idea of elementary row operations. Oops. Right, so usually I think you'll even see the book sort of write it as ERO, right? It's an elementary row operation. All right, and we have essentially 3 row operations that we can do. So we can multiply a row by a constant. So, or non-zero constant, right? I think that's actually a better way. The other one is we can add 2 rows together. And finally, we can swap or interchange rows. Okay. All right. And so the goal is to use these elementary row operations in order to simplify an augmented matrix. Okay. So and I'll sort of write that out. Right, so we're gonna simplify our augmented matrix A prime, where A prime is sort of the joining or the stacking of A and B that are part of our that come from our matrix equation that we're trying to solve. So from AX equals B. So that's what the A and B are, of course. All right, so we have this augmented matrix. Yeah, so if we want to write out the whole thing, so we start off with A11, A21, A1N, and I'm just going to skip sort of a whole bunch of this. Or else I'll just be writing this all day. Right, so we have our A values of the system of equations, and we have this B1, B2, all the way down to Bm, okay? And what we're going to want to do is apply these elementary row operations in order to get something that looks like an identity matrix. All right, so we're going to have a whole bunch of zeros and ones. Oops, this should be a 1. All right, so we want something that sort of looks like that, where this is the identity matrix. And then we're going to be particularly interested in the values that are here, okay, on the right-hand side. So we'll call them B1 prime, B2 prime, B3 prime, all the way to Bm prime. Okay, so if we're lucky, we get this identity matrix, right? Sometimes we won't be able to, but that's what we're going to be aiming for. Okay. And when we don't get it, that will actually tell us something about the solution. Okay, so we can do a quick, well, it's not really quick. I sort of hate doing these problems because they're fraught with error. But what I'll do is I'll show you how some students taught me how to do it in Excel, and I sort of do it in Excel now. But I'll just do it by hand for one particular example problem, just so students can get a refresher, right? Okay, so let's say we're solving the equation AX equals B, where A is given by the following matrix. Okay, so we have that matrix. And we want to apply Jordan-Gauss in order to solve it. Okay, so the first thing we do is, of course, we start off with our augmented matrix. So we're just sort of concatenating A and B together. All right, so what we're going to do is, our goal is to apply these elementary row operations in order to get this block here to look like an identity matrix. Okay. All right, so the first sort of thing that we can do is we can take the second row and subtract the first row from it. Okay, so I'm going to drop this here. I'm not going to write it anymore. So we can go ahead and do that. So the first row stays the same. The second row, we're going to subtract the first row from it. So we'll get a 0 here, -3, 1, and -3. Okay. Next thing we can do is we can take the first row and divide by 2. So we'll have 1, 1, 1/2, 9/2. Right. Now with that, we can use, what can we do? I'll do that. We can subtract the first and third row, so we can take third row, subtract off the first. I think yeah, okay. So nothing happens to the second row. And we're just going to subtract first row, third row. So we get 0 here. -2. 3/2. And 4/2 minus 10/2. 9/2 minus 10/2 is 1/2. Okay. So that's looking better. What can we do next? Let's see. Gosh, I always hate this process. It's never fun. Okay. I don't know. We can take the second row and subtract the third row. Okay. So this will start getting us closer and closer. So we and then multiply times -1. Right, but we can do that in steps. Or is that the best way? Oh, or we could do this. Subtract 2 times the third row. Okay, so that will give us a 1 here. Man, I always hate doing this. 2 times the third row, 3. God, why do people do this by hand? 1 minus 2 times 3/2. -2. I always feel like I'm doing something wrong here. See, this is why I do not suggest anybody does this by hand. -4. Well, why did I even do that?
Excuse me, Professor.
Yeah.
The second row is -4.
Oh, it's not. It's -4. Actually, I don't even think I did the right step here for advancing what I want to advance. I guess you could, because really, what we want to do is cancel out this guy here, right? So let's take a different approach. Actually, I think I did the wrong step. I didn't trust my notes, but I'm going to trust my notes. We'll take this second row and we'll divide by 3, by -3. Okay. That's probably nicer. But thank you for catching that error. There we go, -1/3. 1. That's what I want to do. Okay. Man, what a terrible. I don't know who's. I feel bad for people who had to solve matrix equations by hand when they were before computers existed, right? Yeah, no fun. Okay, so now we can do 2 times the second row plus the third row, and we're going to stick that in there, right? Okay. So again, this all stays the same. But at this point, we're going to take twice the second row and add them. Right? So the goal here is to cancel out this -2. So we get 0 there. Hopefully, if I did my math right, 3/2. That is not. Oh. We get 5/6 here, and we get 5/2 here. Okay. Next step. Ooh. We want to make this guy look like a 1. So we're going to take the third row and multiply it times 6/5. 1, 1, 1/2, 9/2. Mm, 3 divided by 5, 2. Okay. All right. So this is actually a pretty good place to be in. There's a few more steps because what we want to do is get rid of this 1, this 1/2, and this 1/3. But the elementary row operations become a little bit easier to do. But ultimately in the end, what you end up with is the following. Dot, 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 right? Fortunately, I don't really like it when people do dot, dot, dots on their homework assignment. And so Jordan Gauss is not really fun. All right, so the idea is after you do this whole thing, Gauss-Jordan or Jordan-Gauss, whatever it's called, the implication is that these values here are actually the solution to your set of linear equations. So x1 is equal to 1, x2 is equal to 2, and x3 is equal to 3, and that's our solution. Okay, and it's the solution to the original problem, and more so, that solution is unique. Right? That is to say, that is the only solution to the problem, right? Now, there will certainly be cases. So what we're going to do is sort of go through all the cases, right? So if you have a solution, right? So, where did I put it? Oh, I guess I had it in the last thing. So we're looking for 3 possible outcomes, right? So we have one solution, we have no solution, we have an infinity solution, right? So we solved a case where we end up with one solution, right? And so this is kind of what you're going to end up looking like, right? So what happens with Gauss-Jordan with no solution? Well, when that happens, you're essentially going to have an equation that can't be satisfied, right? You'll find one linear equation that can't be satisfied. So in order to show this, we'll start off with sort of a toy example. Okay. So if we were to do this and we were to find that augmented matrix, we'd get 1, 2, 3, 2, 4, and 4. Okay. And we can start applying Jordan-Gauss. And so let's say we took the second row and we subtracted off twice the first row. All right, so that's what I'm going to do. If we do that, there's an arrow. We end up with 1, 2, 3, but then we end up with 0, 0, and -2. Okay, and this is problematic, right? Because what happens is this augmented matrix will always have a representation to a set of linear equations, right? So if we want to figure out, well, what's the representation of this augmented matrix to a set of linear equations, it's still the x1 plus 2x2 equals 3. But now for the second row, we have 0x1 plus 0x2 equals -2. And of course, there's no x1 and x2 that satisfies this equation, right? So there's no solution, right? So the end result, right? So sort of the lesson that we've learned here is that if your Gauss-Jordan results in a row of zeros, with a non-zero value in the last entry, then this implies that you have no solution. Okay, so as you go through when you're sort of learning these problems, all right, so you got no solution if you ever have a whole bunch of zeros, like here, and then a non-zero value, right? If you were to have 0, 0, 0, that's fine. right? Because that's that would be the same thing as saying 0x1 plus 0x2 equals 0. That would certainly be satisfied. But that corresponds to sort of a different case, which is the case of infinite solutions. Okay? So let's sort of talk about a quick example of that really quickly. And then I think what we'll do is I'll sort of show you how we do that, how you can solve these problems in Excel a bit faster. Because there's no reason to do these by hand. I think it just introduces the high probability of making a mistake. Okay. All right, so let's sort of look at, again, we're going to sort of look at Gauss-Jordan. What happens if we have infinite solutions? Sort of funny. This I did not remember before I started teaching this class again, but again, it's been about 20 years since I took linear algebra. Yeah, 20 years. Wow, scary. Okay, so we'll start off with our system of equations. So we want to take a look at our augmented matrix. All right, so we're going to start off with that and sort of work our way through this problem. We'll say, let's take the third row and we're going to subtract off the first row. And again, our goal is to get something that looks like a diagonal matrix. So obviously we want to get rid of that one there. So when we do that, we get 0, 1, 1, 3. Okay. And if we looking at this, we can say, hey, if we take the third row and we subtract off the second row from it, we're going to have a problem, right? So let's go ahead and do that. Because these rows look the exact same, right? So if we subtract one from the other, we're going to end up with a row of zeros. Okay. So this isn't the same as the last case, because in the last case, we said that this last value was non-zero. But in our case, we have 0 all the way across, right? So this is sort of problematic. Right? Now, again, so my view on this is you can always, with Gauss-Jordan, you can always go backwards and forwards, right? Because this is just a representation of the same system of equations, right? So if we were to go backwards, this is the equivalent of saying 0x1 plus 0x2 plus 0x3 equals 0, okay? And this is always true for any real x's. So it doesn't really tell us much. But we are left with a couple other equations that we can sort of work with, okay? So let's sort of see what we're left with and what that tells us, okay? So if we look at these remaining equations, we have something like, again, we're going to sort of go backwards, right? So we have x1 plus x2 equals 1, and then we have x2 plus x3 equals 3. Right? So the way we're going to go about sort of addressing this problem is we can just arbitrarily assign x3 a value, okay? So we're going to say x3 is equal to some value k. Doesn't really matter, right? K can be anything, right? So if we do that, what we end up with is, well, that tells us x2 is equal to 3 minus k. Right? If we then substitute, so we just get that from substituting k in here. That implies that, if we stick in x2 into this top equation, well, that tells us that x1 is equal to 1 minus x2, which is equal to 1 minus 3 minus k. So we can end up saying x1 is equal to k minus 2. Okay, so our system of equations ends up with the following solution, right? So we have x1 is equal to k minus 2. x2 is equal to 3 minus k. And x3 is equal to k, where k is some real number. So k is an element of reals. So how do I think about this? Well, for me, I think about it as this is sort of like a parametric equation. Okay. And so if we have some 3D space, right, where k is one value and then we have x1 and x2, it's going to sort of set up a solution that looks like a line in space, okay? And that line in space is defined by these two equations, right? So for every value of k, I can find an xy, okay? And so essentially what we're doing is our solution lives on a line, and we can sort of slide up and down this line, okay? It's sort of neat. So I have this in the note. Sometimes we can talk about the dimensionality of the solutions. So usually most people will just say, hey, we have an infinite number of solutions, okay? When I was younger, I used to do a lot of work in robotics. And I had this professor who used to always talk about, single infinities and double infinities of solutions, right? And so where does this idea come from? Well, in this case, we have a single infinity of solutions because that infinity is based on x3, right? So we have one value where we can pick anything. Now, you could certainly imagine a case where we end up with something like, 1, 2, 5, 6, 3. Then what if we had 2 rows of zeros, right? Actually, does that even make sense? 1, 2, 3. Yeah, sorry, too many. Let's say we had something like this, okay? In this case, not only do we have one variable x2 that could be a free sliding variable, we have 2, okay? And so this gives us way more options. So instead of a solution existing on a line, okay, the solution actually exists on a plane, okay? And so that's actually pretty neat. And the equation for your plane is going to end up being defined by this guy, right? So that's pretty neat. And so my former advisor would talk about having, in this case, we would say we have a double infinity of solutions, because your solution sort of exists in multiple dimensions, right? So it's sort of like talking about how much flexibility do you have in generating your options or your solution. So I always thought that was sort of a neat way to think about it, because the idea is if you can play with 2 variables, right, especially in an optimization standpoint, right, like playing with 2 variables, you still satisfy some system of equations, then you can choose the combination of the 2 variables that works best for you, right? Well, if you just have 1 variable that you can play with, then you're kind of a bit more restricted, right? So this notion of having a double infinity is actually sort of a fun idea and sort of a neat way of thinking about flexibility in your solutions. Okay. All right. So that's the Jordan-Gauss method. One thing I think that is worth doing is, I think figuring out a way to apply Jordan-Gauss, like using Excel, right? So like, as a general rule, I require you guys to show all your work. So if you just show me the answer after Jordan-Gauss, I'm going to go, oh no, you didn't show me any work. You might as well have cheated. So I'm going to give you 0 points, right? So one thing that we can sort of do is say, all right, can we at least find a way to do the Jordan-Gauss method in a simpler procedure? There we go. Where we're less likely to make mistakes. And so I think it's worth sort of saying, okay, how do we do this in Excel, right? Or if you want, you can do it in MATLAB, but I think a lot of students will use similar ideas when we apply the simplex method. They'll do something similar with Jordan-Gauss. So, what I'm going to do is I'll try to see if I can do it with the same example problem we had. Oops. And hopefully we get the right answer, right? So usually they'll start off with something like this. And, we're going to just try to apply sort of our equations. And I think so this is what I sort of figured out. I never quite figured out because I didn't ask them, but most people would just say like, okay, let's replicate the matrix. Okay. Oops. All right. So we got that guy. Oh, this one. Okay. All right. So they just replicated the matrix again, just by, saying the B6 cell is equal to the B2 cell, and then they're going to fill it across and fill it down. Okay. But let's say we wanted to apply some sort of operation. So we wanted to do row 2 minus row 1. Okay. And what they would do is they just say, well, instead of just saying B3, we're going to subtract off row 1. Okay. And we can fill that equation across. Awesome. That's sort of what they did. Okay. And they actually just sort of keep repeating that process over and over and over again. So I guess the next step here is you take R1 and divide by 2. So again, we can just change this equation, say divide by 2, fill it across, right? And so what I'd get in homework assignments was essentially an Excel spreadsheet that looked like this, which in my book, like you're telling me the important parts, which are what are the row operations, right, that you're doing to achieve your solution. And so for me, I think that's the most important part. So if you're to submit something like this, I'd make it a little bit prettier, right, by telling me what the equation is and what you're satisfying. And, maybe, I don't know, you could just say A prime. Oh, wait, no, this is this. Right, you do something like that. So at least I know what you're kind of talking about. I think people would even make it look pretty, right, which I love. So let me hide this. What would they do? How do I do it? Format table. How do I put the dang boundaries on it? I always know how to do this in other places. Anyways, they would can I do it with a pen? They would do that, right? So you know how you can sort of draw the boundary cells, right? So they would do that. That way I know it's a matrix, right? I think that's always helpful. So I would definitely recommend that. And they just go through the process, right? So that would sort of make life a lot easier, and now you're way less likely to make any sort of mistake, right? So I want to highly recommend everybody do that. So what's the next thing I did? Yeah, R2 divided by -3, right? It sort of propagates down. And of course, you could always do more complicated stuff. So 2 times R2 plus root of 3. So let's do that. Is that the next step? Oops, I'm going to do that. Yeah, right there. That was it. I feel like that's not right. What did I do wrong? 2 times. Oh, I forgot to get rid of. Oops, skipped a step. Root 3 minus root 1. There we go. Yeah, so just go through this process. I think you're way less likely to make a mistake if you do it this way. So I know it takes a little bit more time, but I think in the end you're sort of better off doing it this way. But again, that's my opinion. If you want to do it completely by hand, you are certainly welcome to. There we go. Yeah, so I think that's sort of working through it. So again, that's my personal recommendation, but you can do whatever you want. Right, so let's see. So I want to take a quick 5-minute break. So we'll get restarted until 30. So this will be our last break, and then hopefully we'll get through the rest of the material. So feel free to step away for about 5 minutes and then rejoin the class. Okay, all right, so we're gonna go ahead and get restarted. All right, so recognizing that the Gauss-Jordan method is important, our next sort of step is to start dabbling a little bit into an important concept in the simplex method that has a strong relationship to what we just learned. And specifically, it has to do with this idea of what we call basic variables. No, sure. Basic variables and non-basic variables. All right. So a basic variable is going to correspond to any one second. Is going to correspond to any column that sort of has, is it column or row? That ends up looking like it has a 1 and then zeros below it. And then I think potentially a value. This seems weird. Hold on a second. I was confused. Basic variable. Basic variable. Yeah. Yeah, it's where it's going to have a single 1. Okay, and actually let me write this as a column so it makes a little bit more sense. So it's going to correspond to anywhere where we have something like 0, 0, 1, and then 1's below it, or 0's below it, right? So you're going to see a 1 and then 0's below. That's really the key thing. Okay, and this is going to be important when we're applying the simplex method. All right, so let's sort of see some examples of what I mean to this. Okay, now the cases that we're going to have are going to be cases where we have more variables than equations, right? So if we look back to when we applied the Jordan-Gauss method, okay, here we had sort of like our augmented A matrix is 3 by 4, right? So we had 3 equations, right, and 3 unknowns, okay, and then we had the B, right? So these are B, but really these the columns correspond to the unknowns, while the rows correspond to the number of equations. So when we solve optimization problems, we're usually going to sort of be in a different scenario where we have kind of more unknowns than we have equations. Now, that's not really the case because of we might have linearly dependent equations, but for the most part, you know, you want to think about the columns corresponding to the variables while the rows correspond to the equations, right? So if we look at one example of the Jordan-Gauss, we could still apply it where we might end up with something that looks like this. So we might end up with 1, 0, 0, 0, 0, 1, 0, 0, 0. Oh wow, look, it's, I don't know if you guys can see the transcript, but it actually gets the 1, 0, 0, 0, 0, 0, 0. Oh, neat. I don't know, can I, well, whatever, that's just, okay. All right. Okay. All right, so let's say we have the simplex method and we applied the following, okay? So, oops. Okay. And I'm sort of representing this dashed line to represent what part is the A side and what side is the B side, okay, of the equation, you know, AX equals B. Okay, so the way you want to think about this is each row, so this would be like equation 1, equation 2, equation 3, equation 4, and equation 5. Well, each of these columns correspond to a variable, x1, x2, x3, x4, and then this is the B values, right? So from here. Okay, so of course you know, when we have this, the first thing that we see is, oh, okay, there's no solution. In the case where you have no solution, the idea of basic variables and non-basic variables doesn't really make sense. Okay. So let's look at a case where we do have a solution, right? So, and again, these are we're following the same process that we did before in Jordan-Gauss, where or Gauss-Jordan. In Gauss-Jordan, we went through 3 different options of what does it look like? What does a problem look like if you have no solution? What does it look like if you have one solution? And what does it look like if you have an infinity of solutions, right? So this is the no solution case. Which we're saying doesn't really matter to talk about basic variables and non-basic variables. For the second case, we'll talk about there's one solution, a unique solution. Okay. So maybe after applying Jordan-Gauss, we have the following, or we did have the following, I think. Okay. So again, the way you want to think about it is the columns correspond to the variables x1, x2, x3. And then these are equation 1, equation 2, equation 3. Okay, so in this case, we're looking for the columns where we see a value of 1 and then zeros below it for the most part. Okay. So in this case, we actually have 3 basic variables, okay, that satisfy that sort of property. Okay, so the set of basic variables in this particular case is x1, x2, and x3, while the set of non-basic variables is every other variable. Now in this case, there are no other variables besides x1, x2, and x3, and so the non-basic variables is just the empty set. All right, so our third possible option when we apply Gauss-Jordan is we have multiple or infinity solutions, or we'll just say multiple solutions, but really we mean an infinity of solutions. Okay. So let's sort of look at what that might end up with. So I'm going to write down a matrix where we have that option. Okay, so in this case, our variables are x1, x2, x3, x4, and x5. And you can see that we have 4 equations. So equation 1, equation 2, equation 3, and equation 4. All right, and we're looking for column vectors that look like they're basically columns of the identity matrix. And so here they're pretty easy to identify. They're just the first 3. Okay. So we can see, we have the value 1 and then zeros above and below, right? So that's sort of the key feature. We're looking for just a singular value of 1 and then everything else is 0. All right, so in this case, our set of basic variables is going to be x1, x2, and x3. And our set of non-basic variables is going to be all the other ones. So it'll be x4 and x5. There's no reason that the basic variables are going to be next to each other, right? So I'll just give another example so you can kind of see what I mean. Okay, so let's say we had something like this, but instead we swapped these two rows. So 2, 0, 0, 0, 0. So let's say we had something like this, right? So in this case, our basic variables would be x1, x3, and x4, right? While the non-basic variables are x2 and x5. Okay. And so we're actually going to do this, where this is going to come up later on is when we're applying simplex method, these non-basic variables, we're basically going to split up our variables into two sets. Those that are 0, because we can set them equal to 0. It's like the k, right? We can set them to be anything. So to make life easier, we're going to set them to 0 because they don't matter, or we'll show that they don't matter. While the other variables will be allowed to be non-zero, okay? And so in dividing up our problem that way, it makes life a little bit easier. So we'll say these variables we care about, and these other ones we don't care about. Okay. Alrighty. Okay, so let's see, we got. All right, so the next little bit of this lecture is going to be talking about linear independence and rank and its relationship to matrix inverses. If I don't get through everything, then I'll just I'll continue lecturing, but feel free to drop off. It's not a problem whatsoever. That would be true either way, right? You guys could always come and go as you want, but I'll still continue the lecture. And I just want to make sure we get through all this fundamental math stuff. Okay, so the next thing that we're going to talk about is linear independence. Okay. All right. So where does this come up? So let's pretend we have a set of vectors, v, and so it's going to be v1, v2, v3, all the way to vk. And we're going to assume each of these vectors are row vectors. It's mostly for simplicity. So these are row vectors. Oops. All right. So we can take a linear combination of these vectors, right? And so a linear combination is just, we're going to sort of take a weighted average of these guys, right? So just to give a little bit of a definition. So linear combination of the vectors in V is V the set, right? Is any resulting vector of the form where we sort of say, all right, we're going to take each vector and multiply it times a constant. Okay, and again, these C's are arbitrary values. Okay. So where this becomes important is when we start talking about linear independence and its relationship to the linear combination of vectors, right? So we're going to say a set V of vectors is linearly independent if the only linear combination of vectors that equals 0 is sort of the trivial linear combination, right? Linear combination. Okay, so what does trivial mean? Trivial means the easiest one, which is where all the c's are equal to 0. So put it another way, right? The only solution where we can add up all these vectors based on some weighting of C1, C2, C3 is where, whereas when each of the C's are equal to 0. Okay. So the only way we can add up or sort of combine these different vectors to get 0 is when the only combination is full of zeros, right? That weighting. Okay. Now, conversely, we say a set of vectors is linearly dependent if there's a non-trivial linear combination. Okay. I'm just going to write it out. So conversely, a set of vectors V is linearly dependent if there is a non-trivial solution. So that means at least some combination, there's a C1, a Ci, and a Cj that are non-zero. Okay. Okay. Okay, so let's just see what that means in a sort of easy example or a couple toy example problems. Okay, so let's say we had some set V and we had two vectors in it, 1, 2, and 2, 4. Hopefully you can sort of see like, oh, these just look like scaled values of each other, right? One is twice the other. And so this is a case where we have the vector set V is linearly dependent. Okay, and so we can sort of see that pretty easily. So the question is there a C1 times V1 plus C2 times V2 that equals 0? So this is what we want to find, right? And here, this first guy is V1 and the second vector is V2. And certainly we can find that, right? So we could say 2 times 1, 2 plus -1 times 2, 4. Well, that equals 0. Okay. So here C1 is equal to 2 and C2 is equal to -1. So there does exist values of these weightings where we can add them up to get 0. Okay. And sort of, you know, that's a clear, easy example of linearly dependence, where we see how we can sort of cancel out. Another way you think about it is you can cancel out these vectors by some combination, right? So like I found a way to add them together so that I got 0. Another way you can think about it is, can I add up or multiply some combinations of vectors to get another vector in that set, right? So can I use vectors v1, v2, and v3 to make the vector v4, right? This is all the same idea. Okay, so let's look at an example where we have a linearly independent set. And again, we'll sort of pick the easiest case to sort of look at, which is we have the vectors 1, 0, and 0, 1. Okay? And the reality is there's no way that I can combine these two vectors in order to cancel them out, right? Because the ones are in different dimensions. Okay? It's just not going to happen. Now, we do have sort of a trivial case where if the vector set V contains 0, so again, this is the 0 vector, it is linearly dependent. And this sort of makes sense, right? So let's say I had 0, 0, 1, 0, and 0, 1. Okay. Well, based on what I told you, and again, this will be V1, V2, V3. The question is there a C1 times V1 plus C2 times V2 plus C3 times V3 that is equal to 0? And there is, right? So we could just say C2 is equal to 0, C3 is equal to 0, and I could make C1 equal to 5, right? 5 times 0 plus 0 plus 0 gives me 0, right? And so the fact that I can assign C1 a value, right, a non-zero value and still get 0 back, tells us that for this case, this vector set, because it contains the 0 vector, it's linearly dependent. Certainly there's visual representations of this, right? So, if you have the vector v1, which is 1, 1, and v2 is negative 2, 2. Okay, so this first vector might look like that, and v2 would look like that. We can visually see that they're linearly dependent because they kind of lie on the same line. But more so, another way that you can think about linear independence, or linearly dependent and linearly independent, is if you pick an arbitrary point, okay, can you sort of add up these vectors in order to get to this arbitrary point? And the reality is you can't, right? You can add up, so you could do a C1 V1 plus C2 V2, and you could do that, and for any value of C1 or C2, you would end up on this infinite line. Okay. There's no way that you could choose a C1 and C2, right, using vectors V1 and V2, where you could add up to a vector that gets you that point. Okay, so that's another way of thinking about linearly dependence or independence. I think this has I always thought about it in terms of reachability, and if you've studied control theory and stuff like that, but I don't know if there's a mathematical connection, but I feel like there should be, right? But who knows? Okay. All right, so let's look at the case where, so here we have a linear dependent. That was bad, right? Bad. Linearly dependent. Okay, so let's look at the case. I don't want to say it's good per se, but where we have linearly independent vector sets. Okay. And so we'll just choose the example where v1 is 1, 1, and v2 is 1, 0. Okay. So if we want to draw that out, just another color. So here goes v2. That's v1. Okay. And sort of using that idea of like, can we add up these vectors to get any arbitrary point, right? You could certainly see how you could get this, get these vectors to add up, right? So to get the green dot or the red dot. So the question is, you know, another way we can think about it is there a way that we can find a C1 and C2 in order to get this dot? Now, a lot of times, you know, they sort of set the dot, right? Like the way we defined linearly independence is they set the dot at 0. Okay, and that's just to make life easier. But really, it's equivalent to saying, can I put the dot anywhere, right? But by anywhere, they chose 0 in the definition. But really, you could extend it to be any location. At least, kind of. Well, it's a little more complicated than that, but you could certainly see how you could go, hey, I'm going to move sideways this amount, and then I'm going to add some scaled vector of oops, this is v1, v2. So maybe we can do it a little bit differently. So here goes my dot. So we could say, oh, I'm going to take v1 up to here. So this would be c1, v1. And then I'm going to move over c2, v2, right? And that will get me to the dot, right? That's another way of thinking about it. So I always think about it of like, hey, do your vectors fill the space that they exist in, right? So if they have, if you have two vectors, they should fill up the whole two-dimensional space, right? I can pick any point in this 2D and they fill it up. All right. There's also a close relationship with null space if you want to think about it in this way. Okay. All right. So the next thing that's worth talking about is the rank of a matrix. So it's sort of a new topic. So all these ideas that we're talking about, Jordan-Gauss, basic variables, independence, rank of a matrix, it's going to come back to dealing with the idea of, can we solve a system of equations and what are the solutions? Okay, so usually the reason why we care about linear dependence and independence has to do with rank, right? The rank of the matrix determines whether it's invertible or not. Okay, so if we can inverse a matrix, then usually we can solve a system of equations. Okay, so that's why we're sort of working through all this stuff, right? So again, it's you know, it's all connected in a way. Okay. All right, so let's talk about the rank of a matrix. So let's say we're going to start off with some matrix A. You know, we're going to say it's composed of a whole bunch of row vectors. And again, I sort of I put these little bars just to visually denote rows. And that's for me, not for anybody else. So this AI dot, so the dot is just, it's not indicating a column, right? So, but this AI dot refers to the ith row of the matrix A. So what we can do is we can say, well, let's define a vector set V using these rows. Okay. So actually, we'll just drop the dot notation. So we're going to have vectors A1, A2, A3, all the way to AN. So we're going to define the rank. So the rank of A is the number of vectors in the largest independent, or the largest linearly independent subset of V. Okay, so let me write that down. Okay, so subset just means we're taking some of these vectors out and leaving some in, right? So we're going to take a subset of V. Okay, so let's sort of do a couple examples. Of course, you know, if you ever have a matrix, you can just go to MATLAB or your calculator and just ask, hey, what's the rank of the matrix? Okay, so, you know, computationally, this is something you don't really do, right? It's more important to understand the idea of when a matrix has full rank or not, right? Because if a matrix is full rank, then we know it's invertible, right? If it's not full rank, then we might need to solve a little bit of a trick to solve a system of equations. Okay. All right, so let's do a quick example. So let's say A is just the zero matrix. Okay. In that case, our vector set V has 2 0 vectors. Okay. And there's no subset of V that's linearly independent. All right, so just from starters, we can see that V is linearly dependent because we've got the same vectors here and here. Not only that, if we take a subset of them, right? So let's say I just took the subset of 0, 0, right? So I took the first one, or I took the second one, right? We already learned before that if the 0 vector is in a set of vectors, then that set is linearly dependent, okay? So we know this is linearly dependent, this is linearly dependent, and of course this is linearly dependent, okay? Because there's the 0 vector in there. And so what this tells us is there's no subset of V that's linearly independent, okay? In fact, what we're left with is the only option that's linearly independent in some ways is the empty set, okay? Which has 0 values in it, okay? So this tells us that the rank of A, of this A matrix, is 0. Okay. Do another example. This one won't be as silly. So I think the only matrix with 0 rank is the 0 matrix. Okay, so every other one will have a rank of at least 1. Okay. And of course, I guess we should know, it's sort of implicit that the rank of A is somewhere between M, which is the number of rows, and 1. When A is not equal to the 0 matrix, right? So if it's the 0 matrix, then your rank is 0. But in all other cases, your rank will be between 1 and M. Okay. All right, so let's look at this case where A is 1, 1, and 2, 2. And here we obviously see that these two vectors, right, the top row vector and the bottom row vector, they're linearly dependent because we can sort of cancel each other out with them. Okay, one is just a scaled version of the other. So just right off the bat, we can see that the vector set V of all the row vectors, it's linearly dependent. Okay, so we say, all right, let's take a subset of that, right? So maybe we'll call this, V1 is some subset where we just took the first one. Okay. So we have one vector in this vector set. And the only way that we can get 0, so the question is there a combination of these vectors, which is only one vector, where we can get 0? So this is the question that we're asking. What values of C get us 0? And in fact, there's only one, which is the trivial solution. And so what that means is this vector set V1 is linearly independent. Okay, so that's good. Likewise, if we are to take the second vector and make that a vector set, that's also linearly independent. Okay, so in this case, the largest subset of V that's linearly independent always has one element in it. Okay, so this implies that the rank of A is equal to 1. All right, so we can do one more example with a full rank case. Okay, so here our vector set V is 1, 1 and 0, 1. And we can sort of see there's no combination, right? There's no combination. So if this is V1, V2, or sorry, A1, A2, there's no combination of these two vectors where we get 0 without C1 and C2 equaling 0. Right? We just can't do it. And so what this tells us is that the rank of A is 2. Right? And this is actually a pretty good one where the rank of the matrix is equal to the number of rows and the number of columns. So this is going to be a concept called full rank. Okay. And again, this is probably stuff that you did years ago. But hopefully you can think about it in a slightly different way. Now, right now I'm just sort of looking at these values and telling you, oh, there's rank 2, obviously, right? It's, it's not so obvious. But one way we can figure out the rank of a matrix, right, especially if you have a big matrix, is by applying the Gauss-Jordan, right, in order to figure out the rank, okay? Okay. And so the rank of the matrix using Gauss-Jordan, right, is the number of non-zero rows that you end up with. So if you apply Gauss-Jordan to A, the rank of A is equal to the number of non-zero rows. Okay. And again, this reflects back on what we had already done before. All right, so let's say, you're applying, you have a matrix. And in fact, we don't really care what's in B, right? But, you're applying Gauss-Jordan. So I'm just going to write B1, B2, B3 because it doesn't really matter. Because all that matters is this part right here. Okay, what B1, B2, B3 are equal to is sort of irrelevant. But we can certainly apply Gauss-Jordan here. And in a few steps of Gauss-Jordan, so let's say we take row 2 and divide by 2, and we can take row 3 and we can subtract row 2 divided by 2. Okay. So if we go through that process, we end up with 0, 1, 0. And I'm just going to put primes just to indicate maybe they changed. Right? But in this last row, we're going to end up with a bunch of zeros. Okay. And these zeros is what's indicative of having a lower rank. Right? So normally you would, if you didn't have all zeros, right? If you had values, then you'd say there's rank 3. But in this particular case, Gauss-Jordan, right, applying the process, tells us that the rank is 2, okay? Because if we count the number of rows, we end up with 1 row of zeros, okay? And so we only have 2 rows that are linearly independent. Okay. All right, so one thing that's worth noting, an interesting property about rank, is that the rank of A is equal to the rank of A transpose. All right. Where does this become helpful? Well, it becomes helpful when we start thinking about matrix inversion or matrix inverse, okay? And of course, we're going to use matrix inverses to solve systems of equations. Okay? Okay. All right. So let's sort of talk about what matrix inverse is, and we'll sort of tie this all together, hopefully in a way that sort of makes sense. Okay, so let's say you have some matrix A, and it's n by n, and we're going to require that it's square. Okay. And we're also going to have the matrix B, and we're going to assume that this is also square with dimensions n by n. And we're going to say that the matrix B is the inverse of A. If we multiply B times A, that we end up getting the identity matrix. And not only that, if we multiply A times B, we get I. Okay. If B does exist, right? If there's some value B that satisfies this property, then we typically denote it A inverse, right? So, yeah, A inverse. Okay, and again, this is, I don't mean to bore you guys with stuff that you already know, but hopefully it's more about how to think about it, right? So why is this useful to us? Well, it's useful to us if we end up with some matrix equation AX equals B. We can solve for X by multiplying times A inverse, right? So if we have this equation, we can say if A satisfies this property, right, where if we multiply it times its inverse, we get the identity matrix, then that means we can multiply both sides of this equation by A inverse, right? These two guys will cancel, and we end up getting a solution to the linear equation, okay? Now, where does this relate to rank? Well, a matrix is only invertible if it satisfies two properties. So first, it has to be square. Okay, so it has to be a square matrix of dimension n by n. So it could be 5 by 5, 6 by 6, 3000 by 3000, right? It just has to be square. It can't be rectangular, or it can't be a vector. The other property it has to satisfy is it has to be full rank. Okay. And what that means is that the rank of the matrix A is equal to the number of rows or columns. Okay. But again, it's square, so the number of rows equals the number of columns. Now, I want to end with one pretty neat little trick. What happens if A is not square or not full rank? Okay. And in fact, these almost end up being the same thing. So if you're not square, then you're definitely not full rank. If you're not full rank, you can still technically be square, I guess. But usually that means you could drop some equations and you'd still get the exact same solution. So, you know, not being square and not being full rank, you sort of look similar. Now, depending on the case, it's very common for us to actually try to address problems like AX equals B, where A is not full rank or it's not square. And depending on the dimensions of A and how the data is structured, this actually corresponds to two very important problems. One of them is the least norm problem. So we're basically going to say, what's the solution to this equation where the resulting solution has the smallest norm? Or the other one is the least squares, right? So there's also a least squares solution, which again, this is essentially a linear regression problem, right? So let me sort of set it up for you where we can see how, well, I won't really show you exactly the relationship to least squares, but it does have a relationship. So the prototypical example is you have a bunch of data and you want to fit a line through that data, okay? So in theory, that line should satisfy the equation yi equals mxi plus b, right? So m and b are the parameters of this line, right? So where xi and yi correspond to like individual data points. Now there's no way that we can draw a straight line to go through all these data points. It's just not possible. But we can sort of represent this problem and try to solve it, right? So one way that we can think about it is if we were to write this as like a AX equals B, okay? We could pretend our A matrix is filled up with all of our X data. And a bunch of ones. Okay. And we're going to multiply that times M and B, which are unknowns, right? These are the parameters of the line that we want to find. And hopefully we can find an M and B that when we apply this equation, we get y1, y2, all the way to yn. So we can recover our data points, okay? This sort of makes sense. So if you go through and you multiply row times column, you can kind of see we get m x1 plus 1 times b equals y1, right? So essentially we're replicating what we're trying to do right here. Now, the reality is if you have all these data points that aren't collinear, it's sort of problematic, right? So we have n constraints. So n constraint equations. we have two unknowns. And the reality is the rank of this matrix, so the rank of A, is probably only equal to 2. So how can we solve this linear system of equations that's over-constrained, right? In fact, there is no solution, right? So people sort of came up with this neat little trick, and it's actually the least square solution. So we want to solve AX equals B, but we can't. And again, the way we want to think about it is this guy is A, this guy is X, and that's B. So the least squares problem. And we can't do it because this matrix is not invertible. Okay? This is sort of like a fake equation. We can't solve it, right? But we can do some little tricks, right? So let's say we are to multiply each side by A transpose. Oops, that should be B. Okay. And the trick here is that A transpose A is a square matrix. Okay. Not only that, it's full rank. Okay. So yeah, I might post something that sort of, you can open up a linear algebra book and they'll show you that there's full rank. And the way you want to think about it is, so if oops, basic idea is if you have x1, 1, x2, 1, x3, 1, all the way down, and we multiply it times its own transpose. So you're going to end up with something like this. And 1, 1, 1, 1. All right, so we're going to multiply these times each other. So we're going to take row times column, row times column, row times column, row times column. What do we end up with? Well, you end up with x. So I'm just going to call this row x. So x transpose times x. Then you end up with x transpose times 1. You end up with, again, x transpose times 1, and then 1 transpose with itself. Okay. All right. So you end up actually with a 2 by 2 matrix, which is kind of cool, right? So this value is just equal to 1. This value is equal to the sum of all the xi's. I think this value is equal to the sum of all the xi's as well. And this is equal to the sum of all the xi's squared, okay? And it's a 2 by 2 matrix, okay? And you can actually work it out that it's linearly independent, which is pretty neat, assuming you have enough data. All right, so since we know it's linearly independent, we can actually take the inverse of it, okay? So that means this quantity right here, A transpose X, or A transpose A, is invertible. Okay, so that means we can multiply both sides times A transpose A inverse. So let me move some of this stuff out of the way. Okay, so now that we've done that, because we're multiplying times its own inverse, these two guys cancel out, and we end up with a solution. Okay, so I haven't really explained what the solution is, but this solution ends up being the least squares linear regression, right? So so that's kind of cool. So maybe later on in the semester, I'll sort of show you there's a better proof using optimization. So once we start doing optimization, we'll go back and sort of solve this problem and show that this solution is actually the least squares solution. But you know, for folks who do linear regression on very large problems, right, this is like neat, right? If you have a whole lot of data, all you really need to do is do this A transpose A, and you end up with a, well, in the two-dimensional case, you end up with a 2 by 2 vector. If you have more variables, then your vector, your matrix ends up being larger. But need a little trick. Anyways, okay, so that's it for the lecture. Hopefully you guys learned something new. If not, it's okay. I'm equally happy if you learn nothing, because that means you're coming very well prepared to this class. But hopefully this was a good refresher. Okay, so because apparently it seems that turning down my air conditioner very low worked. We're going to see if that works again next week, maybe. I don't know. If it doesn't, then we'll have to end the lecture short. But hopefully, if it does continue to work, then we can continue to record these lectures live in completion, and I will do it then. So that's it for me today. If you guys have any questions, feel free to unmute yourselves and ask away. Otherwise, I'll end the lecture in about a couple seconds.
Professor, real quick,
Mhm.
do you have any reservations on students having group me's or group conversations?
No, not at all. Go for it. I don't care. I mean, look, the general rule is don't cheat.
Yeah.
Right. That's like saying you guys can't talk to each other, right? So I absolutely have no rule about you guys talking to each other. I don't really care the medium. And in fact, you know, but my concern is if, you know, group me's are being used to share solutions, right, or answers, that's problematic, right? But if it's being used to say like, hey, I'm having a problem with this, like, you know, is there anybody have a hint or want to guide me? That's fine, right? Like you could do that at any point, right? And I do want to encourage you guys to work on your assignments and let me be careful. Every homework assignment should be done individually, right? Like you solved it yourself, right? And you understood the solution. But of course, you know, this is engineering, you guys should be learning together. So find a study group and work through your homeworks together, right? But the end lesson is the homework should be representative of your knowledge, right? And if somebody helps you obtain that knowledge, that's fine by me.
Okay, thank you.
Okay, with that, I'm gonna wrap up lecture. Thanks, guys. It was good seeing y'all. And again, actually next week, I'm almost certain the lecture will have to be recorded because I'm gonna be in the middle of nowhere, I think, with very limited internet. So next week, I'll be traveling, so I think it'll be a bit hard to do a live lecture. I'll try to do it. So I'll try to set aside time, but if not, I'll send a message out. And it'll be the third week that I'll be on campus. So if you guys want to come to lecture, that's perfectly acceptable. But again, expectation is don't sit near anybody. I don't care. Just don't argue with me over it, right? And the expectation is we respect other people's boundaries, okay? And one of my boundaries is don't come up to me, don't talk to me, wear your mask, right? But I'd be very happy to see people in lecture because I haven't seen students in a while. So that's it for me. I'll catch you guys later. Have a good one. Bye.
Thank you, Professor. Have a good one.
Thank you, sir. Bye.
Thank you, sir.
Thank you.
Thank you. Bye.